Tanto non sta registrando. E io ce l'ho. Chiamami al 3812 dal fisso, così è più facile. Sì. Vai, vai. Un attimo. Su, rispondigli tu.
Okay, I think that it's time to start. It's my honor and pleasure to introduce Professor Enrique Dodua from the University of Erlangen-Nuremberg in Germany.
Stiamo lanciando la
and let me briefly tell you something about him. He got his PhD in '88 from the University of Paris 6 under the supervision of Rome. And then his career was stopped. He had three steps in his career. First step in Madrid, second step in Bilbao as founding director of the Basque Center of Applied Mathematics, Beckham. And then he moved in Erlangen a few years ago with the von Humboldt professorship. I mean, he's quite complete applied mathematician because he started working on control for PDEs, then he passed to numerical analysis, and recently also to machine learning. So, I mean, he obtained fundamental results on optimal shape design in aeronautics, also in design of recommendation systems, and also fundamental results on control theory for PDEs. And let me just conclude quoting, I mean, which are at least some of the few awards that, I mean, quoting few of the many awards that he got. First of all, he was invited speaker in the International Congress of Mathematics in 2006, the ICM. Second, he was a plenary speaker to the World Congress of Hyperbolic Equation, IP 2012 in Padua. Then he got an honorary PhD in the University of Lorraine in 2014, isn't it? And he got a 2-year SIG advanced grant in 2010 and 2016. In 2018, he got the von Humboldt professorship. And finally, recently, this summer, he got one of the SIAM Prize. SIAM, for people who don't know, is the American Society of Applied Mathematics. So today, he will deliver us a colloquium on control and machine learning. So, please.
Thank you. It's for me a great pleasure to be here. Of course, I know the city of Bari, the name of Bari for many years, the universities, both the university and the Polytechnic where we are now. I know Giuseppe Coclite as an experienced researcher in PDEs for many years. And since 2.5 years or so, we have Nico Deniti with us in our team in Germany. So since then, we are collaborating more and more. But this is the first time I am in Bari, and I'm very pleased to do it. Especially now that the winter is getting, quite, deeply in Erlangen. So, when Giuseppe told me about this lecture, I thought that it would be maybe better to give a more general lecture that I think is quite, to a large extent, is quite light and easy to follow, but that you can also, through the lecture, you will anticipate, you can guess, you can get an intuition of how deep this can get, right? So as Giuseppe said, I had the honor of receiving this award from SIAM last summer, and at that occasion I gave a lecture and they asked me to write a short article. This is basically one page in this SIAM news, and this is written in a way that is very easy to read, that any educated mathematician can easily go through and understand. So this, for those that want to learn more about this topic, after the lecture you can also have a look to this short article, and of course I will be happy to also interact with you later whenever you want, either in presence or by email. I will be here tomorrow as well, so I will be happy to meet you. Okay? So why putting these two topics together in a lecture, right? So then actually you want to get into this question with some perspective, I think it's good to have a look to how Norbert Wiener back in '48 defined the topic of cybernetics. Cybernetics, automatics, control. Control is a very broad field. Oftentimes, if you talk to engineers, they will tell you, oh, control is engineering. And then there is indeed plenty of, journals in engineering control. But of course, there is a lot of mathematics on it. Norbert Wiener defines cybernetics as the science of control and communication in animals and machines, right? So, and in this very compact sentence, you see at least two binomials, two dualities. Right? The first one is control and communication. So sensors and actuators. So if you want to regulate a system efficiently, you need information about the status of the system, the actual state, right? So for instance, like the thermostat at home. So you need a thermostat that is really a thermometer that is really measuring precisely the temperature, right? And then you need an actuator in order to feed heat or cool air, right? Depending on whether you want the temperature to go up and down. And this is always true. This is when you are driving. I mean, if visibility is low, so no communication, the risk of an accident is much higher. You need visibility in order to drive well. And this applies to everything, right? So politicians are very frequently doing polls about, what is the opinion of people, right? What are the expectations for the next elections and so on. They need feedback. They need information out of the system in order to be able to act on the system, right? So I think there is an opening here. Yeah. So they need information of the system to be able to act on it. So for instance, they will ask to people, what are your main concerns? Then the main concerns of people will be unemployment, will be inflation, will be the energy crisis, will be the war in Ukraine, and then depending on which the priorities are, they can also better define their policies because, of course, the goal is to be re-elected in the next elections, right? We know well. So this is the first binomial, communication and control, right? You cannot do control performing well if you don't have information, if you don't have communication. And the second binomial is animals and machines. Right? So why animals and machines? Actually, this was already indicated by Aristotle 2,500 years ago. In his book of Politics, he refers to the need of humans of building, developing machines that will be able to do the tasks that we as humans are obliged to do on a daily basis, so to be free, right, to dedicate their time to those other activities that are more subliminal and those that we really like to do, right? So then in this way, we have a frigo at home, so we don't need to take care of keeping, food fresh. We know we put them in the frigo, and the frigo is taking care of that. We have the thermostat at home in order to regulate temperature. We have washing machines. We are, nowadays we have automatic cars, even autonomous cars. So all these devices, all these machines are doing tasks that in case we didn't have them, they will keep us busy all the time. And then we will not be, free to do mathematics or to listen to music or to write poems, right, as we like to do. Okay, so then you see there are two binomials here, and when you see these two binomials, this sentence, this compressed sentence, defined in cybernetics, you wonder why this could not be also the definition of, say, artificial intelligence or machine learning to a large extent, right? So at that time, of course, this field didn't yet exist. I mean, there were already a bit later than that, Isaac Asimov in the 60s was already anticipating how the world will be 50 years from then. And this is not an easy exercise. I mean, it's fantastic to read this article by Asimov I think in 68, with the 10 predictions he does for the next, say, 50 years. We could do the exercise nowadays and say, okay, so how will Barry be in 2072? Well, and it's not so easy to guess, right? So you can think on, what could be the challenges of Barry 15 years from now, and how the, the city will be organized by then is not so easy to anticipate. But, Asimov, of course, he was a genius, and he could, of course, anticipate that by, 50 years after 68, I think, so by 2018, people will be able to, to talk to the loved people remotely and see them while talking. And of course, this came much earlier than 2018. We have Skype and all these tools to talk and, video chat for, I don't know, maybe 15 years now or so. Okay? So we could do that exercise. I mean, that will be hard. At that time, as I said, the field of artificial intelligence was not yet existing, not yet mature. But when you see the definition of normal winner, you can say, well, now this could be also the definition of machine learning. So in fact, right, when you think a little bit, when you check a little bit more how mathematics has contributed to these two fields, you see that there is a extraordinary, very, very rich, very wealthy common intersection of goals and also of fundamental mathematics that have been developed in parallel in these two fields, oftentimes by different communities, the same as it happened in control itself, where engineers were working on one side and mathematicians on the other, but oftentimes, cross-fertilizing. And the same can be said about the fields of control and machine learning. Actually, nowadays that there is so much interest in artificial intelligence and in machine learning, right? So actually, when I talk to young people that are, writing a PhD and then they are facing the job market, of course, when you go to an interview and if they ask you, what do you know about artificial intelligence and machine learning? I mean, you cannot say nothing, right? Because then you don't get the job, right? So you have to say something else. Right? There are several, kind of answers you can give, and I think every mathematician, in some sense, knows something about this topic. I was saying the same yesterday about, analysis versus numerical analysis. There are some analysts that say, "Oh, but I don't know anything about numerical analysis." This is not true. I mean, numerical analysis is just analysis, but tracking solutions along a discrete parameter, right? The mesh size or the time step. The same can be said about artificial intelligence. So every mathematician knows a lot about artificial intelligence. The question is, how do you yourself, as a geometer or an analyst or a numerical analyst or a computational mathematician, how do you approach this big and, of course, rapidly growing field, right? So, while the contours of mathematics more or less remain, the volume of mathematicians in the world remain, the rapidity with which, this knowledge area of artificial intelligence is growing is very, very fast. Every mathematician can, penetrate into this moving new, say, agile atmosphere of artificial intelligence and contribute from your own field. Okay? So then I got interested on this topic actually when I went to Erlangen. It was in 2019. In 2019, we were organizing, when I got there, like in the fall 2019, a small workshop on the turnpike property. I mean, the turnpike property, I don't know whether you are familiar with this word, turnpike. I mean, I didn't know. I mean, we were doing mathematics related to turnpike, and we didn't know until one of the referees of one of the papers I wrote with Alessio Porretta, a good colleague and friend in Tor Vergata. One of the referees said, well, you should maybe check whether your results are related to the turnpike theory. I didn't know what turnpike was, so I went to Google turnpike, and I saw, the a highway. Turnpike is like the name of a highway in the United States. And I said, well, what this has to do with the phenomena we are analyzing? It turns out that it was von Neumann, again, always the same geniuses in different fields, like Kolmogorov and so on. So von Neumann, that was analyzing the problem of, say, long-term economic optimal planning, financial, say, economic growth, right, in long horizons. And this is of course, the concern of every country is not about just taking decisions now for the next few weeks because of the energy crisis, but think on the long run, right? So what's going to be the wealth of our country 50 years from now? I mean, what are we, what will the next generations inherit from us, right? He observed that in long time horizons, the optimal strategy was often nearly a steady state. And actually, this is something we are implementing all the time in our lives. Because, for instance, if you have a chronic disease, diabetes, high blood pressure, cholesterol, and so on, you go to the doctor, and the doctor will tell you after all the detailed analysis, they will tell you, listen, you take 1 pill per day, and you come back to, for consultation in 6 months for a new checkup. So they tell you 6 months, 1 pill per day. And then you wonder why a steady state? Why the doctor is not trying to develop a more sophisticated strategy? And then maybe the most sophisticated strategy will be, okay, Monday you take 1,02 pills, and then on Tuesday you take 0,99, and then on Wednesday you take 1,109. Of course, it will be very hard to implement. Will be nearly impossible to do. And the observation by von Neumann is you don't need it. You don't need it simply because if you do it in the long time horizon, the impact, the effect of taking just 1 pill per day will be almost identically performing, optimally as by considering a very sophisticated oscillatory strategy. Okay? That was, this is the Tarpite principle. Later, Paul Samuelson, who got the Nobel Prize in economics, further developed this, original idea of, von Neumann. And of course, this is something that is relevant also for partial differential equations, for the time-evolving models in mechanics, because when you are facing the need of controlling a process, but not doing it in a very short time, but rather in a long run, right? Then you can adopt this idea that maybe you don't need to deal with time-dependent control strategies. You can simply chop off time, consider the steady state model, which is much easier to analyze, compute the optimal, strategy for this steady state system, and then plug it into the time evolving system, right, in a steady manner, because precisely the Tarpite principle guarantees that the results are nearly the same, right? And this is how, for instance, the European Union was designed, right? So I remember very well when Spain had to enter the European Union, right? There was a few years of very stiff, very strong financial diet, right? Because the inflation rate in Spain was 10%, as it is today again, right? Because we lost the Tarpite, right? But it was, for a few years, Spain had to do a very strong economic diet in order to beat this inflation from 10% to, say, 4%, the unemployment rate from, 22% to 8%, and so on. Why? Because we were entering this Tarpite in which the rest of the European economies were operating more or less a steady state, right, where all these macroeconomic figures are kept constant, right? And then once you join this flow, then you are in the crowd. This is like the Giro d'Italia. So Nico is an expert on Giro d'Italia. Right? He's there, right, Nico? Okay, you know something about, biking, and you ask Nico. In Erlangen, everyone bikes. Huh? This is why I'm saying this. So when you are in such a race, if you enter, I don't know how you say in English, el pelotón, right? So the crowd, then it's much easier to follow the track, right? What is hard is that if you are delayed for some reason, right? Because you had, a technical problem, you are delayed, to catch up this 1 kilometer distance with respect to the peloton is very hard. But once you are in, then you are driven, by the flow. Okay, so these are the topics we were discussing, and then there was Daniel Tembrick, a junior professor in our department, who said, "Well, Enrique, but maybe you could have a look to the deep neural networks, because probably these ideas could be of some use." And this is how, starting in 2022, we paid some attention to this And indeed, it's true. There is plenty you can bring from the classical, say, theory of partial differential equations, of ordinary differential equations, dynamical systems, and control in this area of machine learning. And I wanted to show you today how you can do that, right, without, leaving your own field and in an impactful manner. This, as you will see, opens plenty of perspectives of future work. Okay, but now, just one slide. What is control theory? Control theory just by one result. So the one I like the most that everyone can understand is this result by Kalman, right? Rudolf Kalman. That was also basically in the 60s. He was not the only one to contribute to this. These kind of things were done also by Pontryagin, Lyapunov, all the classicals, but he had the genius to write it down in such a compact and easy to understand manner. Kalman said, what could be a general formulation of these problems? Well, it's the same as Cauchy, a Cauchy problem. What is this? So it's just, you can think on a finite dimensional system, n components on a system can be just the temperature on the n rooms on this building, or can be a social network in which you have hundreds or thousands or millions of individuals, doesn't matter. Every individual is X1, X2, each individual has a label, right? And you are tracking the opinion, how the opinion, through interaction, through exchange of information, opinions, and so on, even fake news, right? How this opinion is evolving and is making that people, move from, for instance, one political position of the majority to the other that we see often, on the switchings nowadays in the European governments. Okay, so this, you assume that this system is simply evolving through this interaction matrix Aij is simply telling you how the position, the state, the opinion of the individual Xi is influencing Xj. Is not necessarily symmetric. Oftentimes there are relations in which one person is sending plenty of emails and then the other one is only responding, occasionally, right? Not necessarily a symmetric matrix. And then, oftentimes to control this system, you have some few, say, actuators, right? U of t, but normally these actuators are just a few, right? M. For instance, I will show you later the example of the car, in which basically you are driving the car, which is a very complicated engine with many free parameters, and you are basically controlling the car using two controls. One is the angle, the gear, and the other one is the acceleration. So you have two controls and a very complicated engine. So this is typically the situation where you have plenty of states or components of the state to be controlled, N, but only just a few number of controls that we call here N. Eventually, you can even think on, the magic situation in which a very complicated system could be just controlled by a single finger, right? N equal to 1. Can this be done? Then, well, Kalman said, well, this is a property that will depend first, of course, on how the inner interactions of the system are operating. This is the matrix A. But also on the matrix B. What is the matrix B? The matrix B is simply telling me, right, how the action I am doing with the magic finger is affecting all the components of the system. Probably is not equally the same for all of them, right? So, for instance, acoustic propagation, people that are closer are listening, are receiving the signal with a higher intensity than those that are farther away. So the B is not necessarily a constant vector. It could be that some of the components of the system are much more sensitive, right, to the action of the control. And then he said, listen, if the goal is to control the system, and controlling the system is just checking whether, given an initial configuration and a final configuration, I can drive the system from the initial configuration to the final one by using some smart controls, he said, if you want to do this, the only thing you have to check is whether this Kalman rank condition is fulfilled. So you take the matrix B, assume, for instance, we have just one magic finger, one control. So then B is just a column vector. And then you multiply the matrix A with B, and you get another column vector. And you do this n minus 1 times. So you have here n column vectors. This is a matrix n by n. If the rank of this matrix is full, then you can. Okay. Now, if for some reason you compute the rank of this matrix and what you get is n minus 1, then you say, well, I can control the system, but not completely, because there is one component of the system that I cannot control. This will be the car on space. The car is controllable on the plane. So if there are no obstacles, you let me drive a car, on a big, flat, clean square, and then I can definitely maneuver in order to drive the car from any position to any final position on the plane. But if you ask me to get, go up, vertically, I cannot do with the car. I need an helicopter to do it, right? So this will be the typical situation. For the car, you get rank equal 2, but not 3, so you cannot move in the vertical direction of space, okay? So, and why, just to give you a pseudo proof of this, why such a condition? The reason is very simple. Actually, when you write down the solution of this system using the variation of constant formula, you recall the variation of constant formula says integral from 0 to t of exponential a t minus s b us ds. So you have exponential a times b. Now, what do you do with exponential a? You expand in power series, a to the power 0, a to the power 1, a squared, and so on. So you see, you enchain all these powers of a multiplying b. But here I am stopping at the level n minus 1, at power n minus 1. Why I don't go to the power n? The reason for not going to the power n is simply that, according to Cayley-Hamilton's theorem, every matrix is a 0 of the determinant. So it means that a to the power n is a linear combination of a to the power 0 up to a to the power n minus 1. So I can continue writing here, further columns, but all the new columns I'm writing are linear combinations of the previous one. So I saturate the controllability of the system just computing this rank, and then, as I tell you, full rank, then full controllability, not full rank. So if you miss n by n minus 1, n minus 2, and so on, it means that there is some rigidity on the system. There are some directions in space in which you cannot move. Example, we can run, but we cannot fly. Okay? Now, this, that is a very elementary result, is very nice. I mean, this is a very compact presentation for control. There are some, however, many difficulties related when you want to have a more accurate understanding of this. There was actually a pioneering paper on control by Lord Maxwell, I mean, the same of electromagnetism, whose title is simply on governors. Governor was the regulation, probably the most relevant ingredient in the Industrial Revolution, was this mechanism of rotating balls that was allowing to keep, pressure on the steam engine constant, right? And that was later applied to many devices, like, for instance, the gramophone, right? Because nobody wants to listen music on a gramophone that is rotating with a velocity that is not constant. You need the velocity to be constant. Also, the governor mechanism was later also applied at home in the kitchen with this, I don't know how you say in English, or maybe in Italian, olla a pressione. Pentola pressione. So what is the goal? The goal is to keep pressure inside constant. You don't want the pressure to go too high, otherwise it will explode. And you don't want the pressure to be too low, otherwise it will not be, performing ideally. So you need to keep the pressure constant. So what, in the top of this olla a pressione, there was this rotating mechanism, so that when the pressure was too high, it was rotating too fast, the two annuli will go up, and then we let, the steam to go out, lowering the pressure. As soon as the pressure will lower, the axis will rotate more slowly, the annuli will go down, will fill the gap, and then will preserve again, right? So this is a typical, feedback mechanism whose performance you can essentially analyze by this kind of models. And the main remark of Maxwell was, be careful. Even when, the system is controllable, it is not necessarily the case that if you put more control, the system will perform better. So many control mechanisms, saturate after a given time. And then the example I give always, and here in Italy is very convenient, is like coffee, right? So, people say, some people tell you, I drink a lot of coffee. Okay, A lot is what? 7 coffees per day or 10? Well, I don't know. Depends on the person. But for every person, there is a maximal M. I mean, if you drink too many coffees, right, or too many beers, or too many glasses of wine, you know what happens, right? So there is a first phase in which the situation improves, right? You take 1 coffee in the morning, it was good. I take a second one, but if you take too many, then you will be risking a tachycardia. So there is a saturation threshold, and this means, and this was already observed by Maxwell, be careful, even for systems that are controllable. It doesn't mean that the more you push, the better you will control the system. So this can be analyzed in many prototypical examples. There is this book in '98 by Eduardo Sontag. I mean, you can download the book from the Springer webpage. And here, for instance, he describes the Nelson car. He says, so what is the simplest model for a car? And actually, he observes that the simplest model for a car needs 4 parameters: 2 for the center of gravity, x1, x2, 5 for the angle of the wheels with respect to the main axis, right? So the angle of the main axis of the car with respect to the horizontal line, and then a last angle for the orientations of the wheel with respect to the main axis of the car. 4 parameters, 2 controls, as I said, gear and acceleration. Now, 2 controls allow us to control this 4-dimensional engine, right? In the simplest case, just thinking on 4 parameters. But it's not so easy to do it, and this is why you have to go to the autoescuela, right? You need to get a permit, and for getting a permit, you have to try, you have to learn, right? In particular, parking and unparking is a complicated manner. Why? Because you have to learn intuitively to do these Kalman brackets, right, that are necessary in order to succeed on operating the system. Is the system controllable? Yes. Can you control it? Well, depends. If you learn how to do it, you will. Otherwise, you will never be able to do it. So one example is this one. So this is why the standard permit for driving a car or a motorcycle doesn't allow you to drive this articulated track. So here the exercise is very simple. The track is parked here. And I ask you, please, can you bring the track to this new configuration? But this is the parking lot. So this is the parking. So you cannot exit this parking. You have to do it so that, the track will come from here to here. Now, if you will ask me to do it, I will ask you, please, will you remove these boundaries? Because if you remove me these boundaries, then I can do it, even with my standard permit, right? I will just continue this way. I will go very far, I will slowly rotate, and then I will come back, and then eventually I will be able to place the track more or less in this configuration. But here we are not allowed. There are constraints. So what is the optimal solution to this? This is the optimal solution. And you see, that is not that easy. It is not that easy. This is just a model like Sontag, a bit more sophisticated, because there is the leading, say, engine, and then 2 other ones that are attached. So it's an articulated, say, semi-rigid, say, object in motion. And when you compute in MATLAB the optimal control trajectory is this one here that, as you see, is not so easy to implement, and this is why you better don't try to do it if you don't have the corresponding, say, driving permit, okay? So why is that? It's because not all of us are able to do, what this lady here is doing. This is the Kung Fu parking, right? Okay? And then, as you know, one of the main challenges when getting the driving permit is how to park and unpark a car. And then, as you know, to park or unpark a car, you have to do operations like this. You turn left, you go front, then you turn right, and you go backwards. And you wonder, why I'm doing this? I'm doing the same thing. What is the result of this loop of, turn, go front, back, and then back? What is the output? You come back to the same center of gravity, but the orientation of the car has changed. And if you iterate this a few times, then the car will be free and then you can leave. Okay, so this is one of the most difficult things to be learned. And this is precisely because we are combining the action A1, A2, minus A1, and minus A2. What is the point? Well, the point is that A1 and A2 don't commute. And therefore, you are always gaining, the gap, you are gaining, what the commutator is giving to you, right? So in this case, the lady didn't know. She could just, throw the car, push the car, right, in the direction of the optimal commutator, right? We cannot do that, so we have to operate many, many times. And this is why it's also so tiring to do it. Why? Because the commutator tells you, okay, you will do efforts of the order of epsilon, but because you have to check the commutator, the gain will only be of the order of epsilon squared. So when you have to really gain an angle that is given a priori in order to free your car from the parking lot, then you will have to repeat these, say, epsilon efforts many, many times, because in each step you are only gaining epsilon squared. So to be able to, gain the angle, the say 30, degrees angle that you need in order to free your car. Okay, so this is just to say that in control theory, if the question is, can you, then it might have an easy answer. It might be much more complicated to actually compute strategies that are really, successful when operating the system. And for this, you need, again, a lot of analysis and certainly also a lot of computational mathematics, because as soon as the size of the system is large enough and the system is nonlinear enough, it's very, very hard to get an intuition of how this, say, kind of cascade control is operating, right? So there are then plenty of analysis about this. So to understand what is the canonical structure of a control system, how the control escalates, acting on one component, how it escalates to affect all other components of the system in the so-called domino effect. And then, of course, many questions related to infinite dimensional systems, in which it is even much harder to get an intuition of how, when there are infinitely many components all, interconnected, whether or not the action of a control can be sufficient to effectively control of the components of the system. Plenty that has been done, a fantastic field. Okay. Now, machine learning, we said the goal today is to show that there is a link, right? Unfortunately, I don't have a watch here. So what is the time now?
45.
45. And when do we start? Okay, good. So supervised learning. Supervised learning is probably the simplest problem in machine learning. So it's actually something as simple that you wonder why we should do mathematics for this, right? Because, so here you see the example. So in this exercise of supervised learning, we have to classify trash. Plastic, yellow, glass, green, paper, blue, organic, gray. Everyone can do that. That's very easy. Now, the problem is that it's boring to do it, right? And it's a bit dirty as well. So Aristotle said, you should invent a machine that does this for you so that you can continue doing mathematics. That's the key. So what is a machine? A machine for a mathematician is a function. And it's a function that is doing what? It's taking every yellow object and putting it in a basket, the yellow one. I mean, any plastic item to the basket. Yellow one, every glass object to the green one, and so on. So what can we do? We take all these items, this collection, I think here 8 times 4, 32 objects. They are 32 points. Capital N here is 32. These points are living in an Euclidean space of dimension D. What is the dimension D? Well, you take a picture of every object. So, the dimension of this Euclidean space where this picture is living will be just the number of pixels. It will depend on the resolution of the image, but the dimension is quite high. So you can think that simply every item is just an image in an Euclidean space of a high dimension. Here we have only 32 of them. And I want to build a function that is taking any of these items and allocating to them the label I know. And what is the label? Well, for the plastic ones, the label, yellow, I will say is just -1. For the green ones, it's going to be labeled 0. For the other one is labeled 1. And for the other one is labeled, say, 2. So it's just a matter of building a function mapping Rm into Rn, it could be simply R, right? So that for every item that we already know, we are allocating, we are guaranteeing that the image of this nonlinear function is going to be the corresponding label, the corresponding point in the arrival Euclidean space. So it's just an interpolation result. It's very simple. I mean, you can use polynomial interpolation. What is the problem if you just interpolate like this? Is that, you know, the polynomial you will build will have plenty of oscillations. And what is the goal of supervised learning? The goal of supervised learning is not to do this, but rather to do it in a way that is reliable for generalization. We want a machine that will then be installed in the basement of the building, so that whenever you put an item on this machine tomorrow and, you know, in the future, this machine will be able to recognize whether this is plastic and goes to -1, or whether this is glass and then goes to 0, right? So we need a function that is stable enough so that not only this exercise is well resolved for these 32 items, but in the future, right, the machine has been, say, designed in a way that whenever you put a new object on it, the machine will map the object to the corresponding basket. Okay? Now, in '89, there was a paper by Sivenko. This is the so-called universal approximation theorem. Sivenko said, listen, this class of functions is dense. I will explain you this later, and probably you know already, right? But classes of dense functions we know. I mean, polynomials are dense. This was what? Stone-Weierstrass, right? Or Fourier series are dense. Fourier. So there are many classes of functions that are dense. They are quite oscillatory, all of them. So Sivenko said, there is a new class of functions that is dense. How do you build this class of functions? It's very simple. You take an activation function sigma. Sigma can be the ReLU, the rectified linear unit. This is the simplest one you can think of. There are many others. Let us focus on this one. What is the rectified linear unit? You see also in this that, you know, the machine learning community was not really that of mathematicians, because this is the function simply x plus. This is the function that is taking the value 0 for negative numbers and the value, say, identity for positive ones. 0x. 0x. This is the ReLU, rectified linear unit, x plus, positive part of x. Okay? So, and then he said, listen, if you allow me to take many of these ingredients, right, capital K going to infinity, of course, as usual in density, there has to be a parameter going to infinity. And then you allow me to simply take this sigma and, you know, translate it with the, say, the translation vector, the sheet vector B. You allow me to regulate the slope with this scaling, say, coefficient or matrix capital A. And then you allow me to weight the height, the amplitude of this sigma with suitable bits. Then he said, this set of functions is dense. '89, published in the Journal of Mathematics and Control of Systems, that was launched by Eduardo Sontag, the same that wrote this book in control theory 1 year before. So, you know, at that time, it was quite natural that there was, you know, control and machine learning were more or less the same thing. Things started to bifurcate, of course, with the explosion of, say, computer science in machine learning, where, you know, mathematics were a little bit lagging behind increasingly. Okay, so but then, you know, people said, this is fantastic, because, you know, if these functions are dense, I don't need to think for this supervised learning exercise, I don't need to think on, you know, very sophisticated functions. Let me just take these ansatz and let me work with it. And then if I have to work with these ansatz, actually, the only thing I have to do in order to build this function that will, this machine that will classify trash, the only thing I have to do is to determine how many Ks I need. The more I take, the more sophisticated the machine will be, you know, and then I have to tune the parameters W, A, and B in a suitable manner. And you know how people did it? Just by least squares. What is the goal? The goal is that F applied to each xi takes the value xi. Is very simple. You just take the distance, fxi minus yi, you take the modulus square, you add this for all, you know, the items you are willing to classify, and you minimize. So in principle, the problem is very simple, just minimizing this function in a Euclidean space. So this function is coercive, continuous in a Euclidean space, so there is a minimizer. Yes, but when you try to do that, you face two of the greatest challenges in computational mathematics. One of them is the course of dimensionality. Dimensions here are huge. Many items, complicated items in high dimensional Euclidean spaces, many terms needed here, many parameters to be manipulated, the course of dimensionality. And the other one, the other difficulty you encounter is that even if you formulate this problem as a least square problem, because sigma is nonlinear, the optimization problem you get is not convex. There are many local minima, and you are really interested on something that is either the global minimum or close to the global minimum. And this might be very hard to achieve. Of course, people then said, listen, what do you do? I mean, if you are an analyst, of course, if you are deep in optimization, you will have plenty of already ideas. But if you are an analyst facing this kind of problems, you will say, well, I apply gradient descent. And because I know that gradient descent has the tendency to get trapped on local wells, I will use a little bit of, say, Monte Carlo, right, in order to get out of these wells in which I am trapped and try to explore other wells that probably are deeper. So stochastic gradient descent, okay, which is one of the most fundamental tools in artificial intelligence. So it was from the very beginning papers by Eduardo Sontag, Sussman on this area, later further popularized by, in particular, Wayne and Yi, 5 years ago. And so people said, well, why don't we try to do the effort that, Sivenko was trying to do just in one shot, building this very tall column, piling up many, like in a, in a wedding cake, right? Many layers, rather than putting many layers, right? Why don't we try to do it incrementally, little by little? And then, these residual neural networks were tuned. And this is indeed very natural for a mathematician, in particular from someone with experience in dynamical systems and in continuum mechanics, right? They said, listen, let's do it incrementally. What does it mean? I take all these pictures that are living in a large dimensional Euclidean space, and let us move all these pictures that are points in this Euclidean space step by step, gradually, so that each picture goes to the corresponding basket. How can I do that? Well, very simple. I built this discrete dynamical system in which every picture, in the position it is after, say, kth iteration, it will move in the next iteration to a configuration which is just a mild deformation of the previous one, in which with a small parameter h here, I apply, this, say, neural network, right? Just a single, perceptron, associated to the sigma, just one shot. And then people said, well, but then if h is very little, so think that h could be called delta t, this is just the time discretization of this ODE. And then people said, well, then we are in the field of control, except for the fact that the nonlinearity here is this ReLU nonlinearity. It's not the typical nonlinearity that you encounter when building, the model for the car, which is full of trigonometry, of course, and there are many trigonometric functions in the nonlinearity. It's not the quadratic nonlinearity you encounter in Navier-Stokes. It's just a very special nonlinearity, ReLU, that for an analyst, a bit striking, but it's fine, it's acceptable. It's a Lipschitz nonlinearity, so this Cauchy problem is well posed. And now the goal is, listen, think on this as a control problem in which your controls are BT, AT, and WT, and choose the controls in such a way that this dynamical system, from the initial time 0 to the final time, will do the magic of taking all these items that in principle are disordered, and then, like in the Disney movies, right, they will travel in space and they will each land in the corresponding destination. So this now becomes a huge problem in which I'm not doing as in the classical control theory. Every time you give me a new item, I change the controls. But now the controls have to be designed so to solve these simultaneous or ensemble control problems in which all the particles simultaneously will flow to get to this corresponding destination simultaneously. This is the big jump that we are doing. So we were able to reformulate the supervised learning problem as a control problem, but we have to pay two prices. The first one is there is a nonlinearity here, which is the ReLU. And the second price is we have to be able to coordinate, the control so that it's, successful for all the particles simultaneously. Now, this can be done. So these are papers we wrote, in particular with Dominic Ruiz-Valet, who got a PhD with us after a master in L'Aquila, and he's now a postdoc in Imperial College. Borjan Esteve, who got also a PhD with us, now he's a postdoc in MIT. Carlos Esteve, who got a PhD in Paris, was a postdoc with us. He's now in Cambridge. And Dario Piguin from Rome, master in Tor Vergata, that was a PhD with us. Now he's working in the Basque artificial intelligence company Sherpa in Bilbao. Okay, so the papers are there. My claim is this can be done simply because the Rubik cube can be solved. So I personally not able to solve the Rubik cube, but I have seen my daughter doing it, so I know this can be done. Okay, so how do you solve the Rubik cube when you see how people do it? Is anyone here able to solve the Rubik cube? No, I mean, don't be shy. I'm sure there is. Nobody here solved ever a Rubik cube? You did it. How you do it? How you do it? You take a Rubik cube. Half of the Rubik cube, part of the Rubik cube is frozen. So you are right-handed, you will fix, part of the Rubik cube with the left hand, and the other one will rotate in a strategic manner. Why I'm saying that controlling, for supervised learning is the same as the Rubik cube, because what is the goal in Rubik cube? The goal in Rubik cube is that every color goes to a face. So it's the same as saying every item of a specific nature, plastic, goes to the basket yellow. So you could say that is the same. These are just the items you are trying to classify in supervised learning. And because you have to do it in a coherent way, you have to make sure that every face, according to the color, every mini face, according to the color, will go to the same big common face, right? And then I repeat, how do you do it? Fix half of the, Rubik cube, turn the other, do it strategically. And then after you have done the rotation, you stop, you watch the cube again, then you fix another half and you rotate the other half, and then you do it in a piecewise constant manner. And a finite number of control actions suffices to solve the Rubik cube, which is a simultaneous or ensemble control problem. Okay? This can be done. Of course, the world champion will do it in 10 seconds. So Gianluca, how long did you need it? 1 minute or? Okay, yeah, so if you do it in 1 minute or 2 minutes, this is already very good, right? But the world champion will do it in 10. What are the tricks to be the world champion? First, you need very fast fingers, but not only this, you also need to compute the optimal trajectory so that the number of motions is minimized. Because if you do too many motions, even if your fingers are very fast, you will not invest the minimal time. Okay? But this is like, driving the truck. You can do it, yes, but I will do a very long loop and I will need a long time. If you want to win the race, then you have to do it, in a smart manner. And things work. Let me show you why it works. So this is a simulation done by Borjan. You have here a cloud of purple, green, and yellow. You compute the controls, you run the simulation, and this is what you see. You see, more or less, the purples go with the purples, the greens go with the greens, and the yellows go with the yellows, right? It works. So now the question is, how do we explain mathematically this? We have three ingredients. We have the control theory, classical control theory. We have the Rubik cube. We have the, Sivenko's ansatz, the sigmoid that indicates that we should definitely be able to do it. And we have the movie. We have 4 ingredients. The movie like a verification that it works. How we do it? Let me just explain you very briefly. You will understand this rapidly. This is where you understand the nonlinear nature of the problem and why, in particular, the sigmoid is possibly the best possible, say, activation function you can think of for this exercise, and why this is very close to the Rubik cube. How do we do it? Just think on this ODE, forget all the rest. So now let me explain you the notation a little bit so that we are on the same page. X is a vector in dimension D. It's just the space of images, x1 up to xd. This is the ODE time derivative of x equal to all this. Now sigma is just recall the very trivial function 0 and then linear, global ellipses. B is a number. You can take it positive or negative, right? At any time t, the ODE is very simple. X prime is equal to wt sigma of at dot xt plus bt. Bt is a scalar. At is a vector. At is the scalar product of, this here is dot, is scalar product, is this vector at times xt. This is a scalar. So a scalar plus a scalar is a scalar. You apply sigma. The sigma is like a guillotine, to the left is just 0. The rest is preserved, is identity. And then the W, again, is a vector in which W plays the direction of the wind. It's a column vector. So eventually, what do you have here? Take any choice at any time t now. You make any choice of B, A, and W. And then I check what this dynamical system is doing. There are 2 possibilities. What is AX plus B? It's just a hyperplane in the space. It's an equator. It's just dividing the space in 2. The same as in the Rubik cube, you decide to divide it in 2 halves. You can choose this hyperplane where you want, orient it as you like, and place where you want. Then, depending on whether you are in one hemisphere or in the other, if you are in the negative hemisphere, sigma is 0, and therefore the velocity of x is 0. So the particles in this half of the space will not move, and the others will move. In which direction they will move? They will move in the direction of the wind. So the only thing you need in order to solve this exercise, you need very, 2 smart persons. One is cutting, the space into 2 halves strategically, and the other one just introducing the direction of the wind. If you do that properly, in a piecewise constant manner, you succeed. So you can, for instance, generate motions like this, where you say, if this was Earth R2, I will say the hyperplane is just the equator horizontal, the south is frozen, and then the north can flow in the vertical direction to the west, to the south. But you can, of course, generate also oblique hyperplanes and oblique directions of motion. So what is the proof? The proof is just inductive. You give me n items, capital N, regardless of what the number of them is, in a Euclidean space of dimension bigger than 2, because in dimension 1 they will collide otherwise. You need room, right? In dimension 2 or higher. And then I can always classify them with a control that is piecewise constant. How do I do it? By induction. So let me just show you one step in the induction. So this is the typical configuration in which, you have to put order in the children's play room. They have toys of color blue, red, and green. And you have to